Welcome to the Problemas channel Season 2 episode 26, the episode which I titled Finite Integer Sums via Scope Expansion, because in this episode, precisely using the scope expansion problem-solving approach, we will describe a wholesale method according to which an alternative expression for any finite sum of integers in the shape shown on the blackboard behind me can be found. Before we do that, however, as a traditional and friendly reminder, if you're joining our channel mid-season, then first of all, thank you very much for your vote of confidence and welcome to our channel. And second of all, it is a good idea for you to go to the homepage of this channel and in the channel's trailer section, find the episode titled The Problemas Channel How To. Watch that episode in its entirety, follow all the instructions that we give in that episode, because in that episode we explain and motivate everything that we do on this channel. In the mathematical problem S2E26, we were asked to use precisely the scope expansion problem solving approach in order to come up with a wholesale method which would allow us to always construct an alternative expression for the finite integer sums in the shape that are shown over here. For example, the finite sum S1, we can refer to the sum S1 as the sum of consecutive whole positive numbers, each of which is raised to 1 and the same fixed first power. The sum S2 will be the sum of the squares of first consecutive whole positive numbers. In other words, we take a set of whole positive numbers 1, 2, 3, 4, 5, raise each and every such number to 1 and the same fixed power 2, and then we want to know what is the alternative expression for such a sum. And we can go on like that in a similar fashion. For example, the sum S3 is the sum of cubes of first n consecutive positive whole numbers. The sum S4 is the sum of the fourth powers of the first n consecutive whole positive numbers, and so on. We also know that the alternative sums or the alternative expressions for such finite integer sums can be obtained in various ways, and we actually discussed one such way in our previous episodes where we borrowed the notion of center of mass from physics in order to do such a deduction. But in this problem and in this episode, we're specifically interested in how the scope expansion problem-solving approach can be applied to the process of recovering the shape of an alternative expression for such sums. Very well. If you were trying to solve the mathematical problem S2E26 on your own, as we explained it in Season 1, Episode 2, then you were expected to come up with the following idea. In order to recover an alternative expression for an arbitrary finite integer power sum that has the following structure shown over here, SP is the sum of whole positive consecutive numbers k raised, each of which is raised to 1 and the same fixed and given ahead of time integral power p, where p can be 1, 2, 3, 4, 5, and so on, where k varies between 1 and n, we can execute the following four-step algorithm. And in a minute, I'll explain where exactly in that algorithm do we use the scope expansion problem-solving approach. As such, the first step of our algorithm is to take the expression n plus 1, raise it to the power p plus 1, and then binomially expand that expression. Step number 2 is to take the expansion that we produced in step 1 and iterate it n minus 1 times by replacing n with n minus 1 in each consecutive iteration. And for those who do not know what does it mean to iterate an expression, I'll explain it in a minute. In the step number 3 of our algorithm, we are to sum the resultant n equations and witness an avalanche of favorable cancellations of common terms that will appear in the constructed n equations. Finally, after all the cancellations are carried out, in step number 4, we are to solve the whole and the sole equation that we obtain as the result of the cancellation of many terms for the sum Sp that is sought after. And in order to produce an alternative expression for that sum, all we have to do is the last step is to substitute the alternative expressions for all the previously evaluated or computed finite power integer sums, Sp minus 1, Sp minus 2, Sp minus 3, and so on, for however many such intermediate sums are in the expression or in the equation for the sought after sum Sp. As usual, with pretty much any things in mathematics, theoretical physics, and computer science, whenever we hear a new material on the first reading, that new material seems to be very scary, very complicated, and very important. But the moment we step up close and personal and begin working with that material, it becomes less mysterious, less complicated, and less important. As such, together, we will apply this algorithm, the 4-step algorithm, to the evaluation or to the process of finding an alternative expression for the first 3 finite integer power sums, S1, S2, and S3, and we will begin our demonstration with the very first case when p is equal to 1. In this segment, we will apply the algorithm that we described in the previous segment to the process of the recovery of an alternative expression for our primitive or base power integer sum S1, shown over here, where the variable k that runs between 1 and n is raised to the first power, or the case when p is a number that is known ahead of time, is equal to 1. As such, the step number 1 of our algorithm requires that we take the formation shown over here, n plus 1, and raise it to the power of p plus 1. In our case, p is equal to 1. Consequently, p plus 1 is equal to 2. As such, as the first step of our algorithm, we are to binomially expand the expression n plus 1 squared. We will take it that everyone who is watching this episode is familiar with what a binomial expansion of an expression shown on your right hand side is. If you do not know what a binomial expansion is, then simply take a pen, take a piece of paper, and multiply this expression over here, n plus 1, by itself that many times. For example, n plus 1 squared will be equal to n plus 1 times n plus 1. Collect all the like terms, write the final expression, and voila, you have a binomial expansion required. In our case, the binomial expansion of the expression n plus 1 squared becomes n squared plus 2n plus 1, shown at the very top of this table over here. Before we move on anywhere else, before we proceed with the discussion of how this algorithm works in the case of the finite integer power sum S1, I would like to point out the place where we use the scope expansion problem solving approach. In this case, we use the scope expansion problem solving approach precisely over here in this step shown over here, and we use the scope expansion problem solving approach exactly twice. Why is that? Well, observe that all our finite integer power sums run till the proverbial number n. S1 runs for the variable k changing between 1 and n, in the sum S2 for the sum of squares of consecutive whole positive numbers. We also run vary k between 1 and n, but the sum is 3, 1 and n, sum is 4, 1 and n, and so on. Here, however, in our algorithm, we, seemingly asking for more trouble, are looking to expand the scope of the work that we have to do. In other words, instead of seemingly working with the sum that runs from 1 to n, we are trying to work with the sum where the variable k runs from 1 to n plus 1. So over here in this addition n plus 1, we use the scope expansion problem solving approach the first time. And where do we use the scope expansion problem solving approach the second time? Correct. We use the scope expansion problem solving approach for the second time over here as well when we increment the given fixed known ahead of time power p also by 1. Notice that in our sums, if you guys remember the shape of our sum as p, that is sum k p, k varies from 1 to n. When we say that the whole strictly positive number p is fixed and it is known ahead of time, then that means that the value of p can be 1 for all the summands k, or 2 for all the summands k, or 3 or 4 or 5. That number remains 1 and the same throughout the sum. In other words, that is precisely what it means when we say that the value of the whole positive number p is fixed. It does not vary over the sum. And that is reflected in our notation over here. The sum S4 is the sum of the fourth powers of k. The sum S3 is the sum of the third powers. The sum S2 is the sum of the second powers, and so on. And that precisely means that the power p over here remains fixed for the duration of the sum, so to speak. However, in our algorithm, again, perhaps counterintuitively, we're asking for a seemingly more complicated work to be carried out, or, in other words, we expand the scope of the local material, and instead of working with the given fixed number p, we work, seemingly again, with a more complicated or expanded material that we refer to as p plus 1. So these are the two places where we use the scope expansion problem-solving approach. Now that we understand how the first step of our algorithm is carried out, we carry out the second step. And what does the second step of our algorithm prescribe? The second step of our algorithm prescribes that we take the expansion that we obtained in the step number 1 and iterate it n minus 1 times by replacing n with n minus 1 uniformly in the expansion produced during the step number 1. And the phrase iterate something means that we take that something, make a copy of that something, and in the new and freshly minted copy of that something, we uniformly or everywhere replace certain material with an agreed upon ahead of time rule. In our case, the rule is to replace the value of n with n minus 1 in every new copy of our original expansion. In other words, for our first iteration, we take our expression that we obtained in the first step, the expansion shown over here, we'll make a copy of it, and then in that copy, uniformly or anywhere where we see n in that expression, we replace the value of this n with n minus 1. For example, in the first parenthesis over here on the left-hand side of the equal sign, what we will have? N minus 1 plus 1, minus 1 and 1 cancel out, we obtain n squared shown over here. On the right-hand side, we also see n. Remember, uniformly means everywhere where we see the symbol n. So on the right-hand side, when we see the value of n, we replace n with what? N minus 1. Boom, here it is, n minus 1. Next summand. Here in the original expansion we see n, in the copy we see n, but we replace that n with n minus 1. We move on to the next summand. The next summand is 1. There is no more variable material, we stop. What do we do next? We make another copy of our original expansion shown over here, and in that copy, again, uniformly throughout all the instances of n, we replace n with what? N minus 2 this time. Or if you will, we can make a copy of the immediately previous expansion, and in that copy replace n with n minus 1, and that perhaps is more straightforward and requires less computational work. What used to be n in the previous expansion becomes what? N minus 1 in the next one. Here it used to be n minus 1, now it becomes what? N minus 2. Again, here something used to be n minus 1, replace n with n minus 1, minus 1 and minus 1 minus 2, n minus 2, move on to the next summon, no more variable material, we stop. We take this expansion over here as our new current expansion, and in that when we make a copy of that expansion shown over here, in that copy we replace n with n minus 1, and we obtain n minus 2 on the left hand side of the equal sign, jump over the equal sign to the right hand side, and again we step through all the summons in that expansion and replace n with n minus 1 uniformly everywhere we see n, and thus we obtain n minus 3 for the first summon, n minus 3 for the second summon, no more variable material, 1 survives the iteration as is, and we keep going in that fashion. We repeat that process of copy and replace n with n minus 1 times. N minus 1 plus the original expansion gives us how many equations? N. And because all our sums are finite, that means that eventually we will run out of material that we can iterate. And where will this point be? Well, evidently when n reaches 1, so k equals 1 corresponds to n equal to 1, and this is our material over here, 1. On the left hand side we will have what? We will have 2 squared, and consequently we'll have again 1 attached to 2 as a factor, and plus 1 summoned will survive unchanged. This is our step number 2. What does the step number 3 of our algorithm require or suggest? The step number 3 of our algorithm suggests that we sum all these equations, sum shown over here, and we witness an avalanche of favorable cancellations. What are these cancellations? Well, I hope that you already see that in our case, the way I formatted our equations, the cancellations will run which way? Northeast to southwest in cardinal directions. Northeast to southwest. In other words, when we sum all the equations on the left hand side, we will have all the terms shown over here. On the right hand side of the equal sign, one final equal sign, we will have all these expressions shown over here, all the summons. And what does that mean? That means that again, northeast to southwest, we do all sorts of wonderful cancellations. In other words, n squared on the right hand side in the northeastern corner over here will get canceled with the n squared on the left hand side of the equal sign that sits in the southwestern corner over here. What about the next cancellation? Well, n minus 1 squared, n minus 1 squared. Would you agree? Wonderful. Next cancellation, n minus 2 squared, n minus 2 squared. Next cancellation, well, n minus 3 squared, n minus 3 squared over here. What about this guy? Yes, he will cancel with the last equation over here. And what terms will survive as the result of these wonderful and favorable cancellations? Well, let's write it down over here. I will put a big line underneath this. So once we sum and cancel, what do we obtain? The only term that will survive on the left hand side of the equal sign will be what? The only term that will survive on the left hand side of the equal sign will be n n plus 1 squared. What will we have on the right-hand side? Well, on the right-hand side, let's work with this leftmost column first. This summand is gone, this summand is gone, all these summands are gone. What's left? Only this guy, it will be left. 1 raised to the second power is 1, so we will have 1. Then what will we have? Observe that the factor of 2 will be common for all these summands. 2 times, 2 times, 2 times, 2 times. So when we sum these guys over here, well, I will group them in a second. What will we have? We'll have plus 2 times over here. What will it be if we spell the summands from top to the bottom? It will be n plus n minus 1 plus n minus 2 plus and so on plus 1. So far so good. N plus n minus 1 plus n minus 2 plus n minus 3 whittled all the way down to plus 1. It's this one right here, this plus 1 right here, plus what else? Plus 1 plus 1 plus 1 plus 1. So these ones is 1 plus 1 plus 1 plus and so on plus 1 will be repeated how many times? Precisely, these will be repeated n times. Now, let us step back a little bit and look carefully at the result of all these seemingly horrible manipulations, but they're not actually that bad once you understand what is going on. N plus 1 squared, we will take it as the fodder, as the material that we work with. We forget about this guy. We know what it is. We know how to compute and evaluate. We don't touch it. Let's concentrate on this sum over here. What is this guy? What is this guy? Well, this guy, if we look at the result at this sum, top to bottom, this is our sum S1 spelled backwards. N plus n minus 1 plus n minus 2 plus n minus 3 plus 1. And if we look at the sum this way, top to bottom, this way, then it will be precisely our sum spelled in the way that many people are used to spelling this sum. 1 plus 2 plus 3 plus n minus 3, n minus 2, n minus 1, bam, and our sum terminates, game over. In other words, we have known material 1 plus 2 times S1, and what is this? N, known material. Thus, we arrive at the step number 4, and the step number 4 of our algorithm prescribes that we do what? The step number 4 of our algorithm prescribes that we take the resultant expression or the resultant equation that turns out to be linear in the sum S1, and we solve that equation for S1. So now I will take a short break over here to erase this material. I'll rewrite this equation shown on the bottom so you guys can see it front and center, and we will fight it out with that equation as the final step. Very good. In the previous segment, we arrived at the equation shown over here on the left-hand side of your monitor, and at the bottom of the board, I intentionally made a sucky job at erasing the string of symbols shown over here that we obtained in the previous segment, specifically so that we'll all understand where this equation shown on top came from. In other words, as the result of expanding the expression n plus 1 squared binomially, iterating that relation n minus 1 times by replacing n with n minus 1, summing the resultant n equations, and performing all the cancellations, we arrived at the final equation shown at the bottom, and that equation has the following form. On the left-hand side of the equal sign, we have n plus 1 squared, n plus 1 squared. On the right-hand side of the equal sign, we have 1, this is 1, plus 2 times the sum of consecutive numbers that decrease technically by 1 starting from n, and that is exactly our sum sought after S1, plus 1 plus 1 plus 1, n copies of 1, which again sum to n, shown over here. And this is the origin or the source of this equation and the genesis of this equation. And remember that the step number 4 not only suggests that we solve the resultant equation for the sum sought after, but we also roll through the right-hand side material that sits on the other side of the equal sign with respect to the sum S1. And for all the intermediate or previous sums, SP minus 1, SP minus 2, SP minus 3, we substitute these sums with their own corresponding alternative expressions that were evaluated or computed previously. In our case, when P is equal to 1, what is P minus 1? Well, let's write it down officially. P minus 1 equals to 0. And what does the sum S0 will look like? The sum S0 will look like K raised to 0 each time, each sum. This is basically n copies of 1, and that is precisely n. This is precisely n. So in that sense, we can replace, once we all understand where this expression came from, we can technically say this is S0. This is our sum, which in some sense does not require any algorithmic effort, if you will, to evaluate on the one hand. On the other hand, in grown-up mathematics, in this string of symbols, in this string of additions, 1 plus 1 plus 1 plus 1 n times, we can recognize what? Excellent, we can recognize the so-called John von Neumann successor function. That is the grown-up mathematics term, but we take this result to be available to us immediately, even though I guess it could be a fun exercise to see if we can roll this sum over here through our algorithm, in which case binomially expanding n plus 1 raised to the power of 1 does not really give us much. But in any case, this is the equation that we have. We all understand where did this equation come from. And now, on the one hand, I do not want to insult your intelligence and show you how to deal with this equation. This is a typical kindergarten variety linear equation in S1, and the moment you see this, you do not need Roman anymore. On the other hand, because we want to be the honest citizens of mathematics, we want to show how the manipulations are carried out, because my stance is that in mathematics there are no secrets, but there are plenty of mysteries. And on this channel, we want to take some mysteries out of what we do in mathematics out a little bit and show in public how these mysteries unravel. As such, we solve this equation for S1 and we obtain 2 times S1 is what? N plus 1 squared minus 1 minus S0, and in some sense, game over here. We divide both sides of this equation by 2, and we obtain our answer. This is an alternative expression for the finite sum S1. Some people refer to these alternative expressions as closed form expression, but again, amazingly enough, in grown-up mathematics, it's not really that straightforward to understand and agree upon what is a closed form expression. But according to step number 4 of our algorithm, in this final expression, we're to roll through it and substitute all the previously evaluated finite integer power sums with their own alternative expressions. In this case, there are only one previous, or in the only one intermediate power integer sum is S0. We know that S0 is basically n, requires us exactly 0 algorithmic effort to come up with that expression. We know this is n, so we spell out n squared plus 2n plus 1 minus 1 minus n. Minus 1 and plus n cancel out, minus n and 2n cancel out, leaving n. So what do we have here? We have n squared plus n left over. So let's write it down. 2 times S1 is equal to n squared plus n. And from that, it follows what? Divide both sides of this equation by 2 and possibly factor out one copy of n from the right-hand side of the equal sign and obtain S1 is equal to n times n plus 1 over 2. This is our final result. This is what we were expecting to produce. And I will repeat this several times just to drive this point home. But as we explained in Season 1, Episode 2, where we described a correct way to practice mathematics, every time you solve a problem in mathematics, theoretical physics, or computer science, we suggest that you step back and try to separate or filter out your experience, your solution into two relatively neat, distinct piles. Mathematics, not mathematics. In this case, what was mathematics, what was not mathematics? Well, we can definitely say that not mathematics was everything that we did in the immediately previous segment, where we shuffled some symbols and where we carried out the so-called finite computations, because in these finite computations, all the life, all the joy of improvisation, all the joy of creativity, all the joy of exhibiting your ingenuity was completely sucked out of. It was not present. The intellectual voltage in following the steps that were templatized by someone else is exactly zero. It was not really that interesting. Consequently, just about the only thing that was real mathematics with a capital M, or a dress rehearsal of grown-up real mathematics, was the very process of inventing, discovering, generating, synthesizing, constructing, pick your favorite verb, the algorithm that we described in one of the previous segments. The process of try, fail, try, fail, try, fail. Maybe this will work, maybe this will work. Try several things, combine them, and then eventually notice the tactical convenience or the tactical power of the binomial expansion. Produce multiple copies, sum them up, cancel out, produce an equation that is nice and kindergarten variety equation that is linear in S1. This is not a, God forbid, nonlinear differential equation in partial derivatives. This is not an integral equation. There are no Fourier transforms, Laplace transforms. There is nothing going on, nothing fancy. Kindergarten variety, solve for S1, substitute S0 with its alternative expression shown over here, and voila, game over. So the idea of constructing that, or the process of constructing that algorithm, was a dress rehearsal of real grown-up mathematics. Everything else that followed was computational calisthenics at best, and definitely was not mathematics, or maybe lesser mathematics. Now that we understand how this algorithm works in the case of the finite integer power sum S1, let us see how this algorithm will play out when we will take on the process of recovering the alternative expression for the finite power integer sum S2. Wonderful. In this segment, we will apply the algorithm that we described at the beginning of this episode to the process of recovery of an alternative expression for a finite integer power sum S2 shown behind me on the board. Because we went very slowly and thoroughly in the previous segment, in this discussion we will step a little bit faster. As such, according to our algorithm, in step 1, we take the expression n plus 1, raise it to the power p plus 1, and in this case p is equal to 2, p plus 1 is equal to 3. Consequently, as the step 1 of our algorithm, we binomially expand the expression n plus 1 raised to the third power. That expansion is shown on top over here. N plus 1 to the third power is equal to n cubed plus 3n squared plus 3n plus 1. Step number 1. Step number 2. We take our binomial expansion, iterate it n minus 1 times by replacing n with n minus 1 in each consecutive iteration. And for example, in our first iteration, we make a copy of the first expansion and we roll through that expansion like in the bulldozer. Every time we see the symbol n, we replace it with n minus 1. Consequently, n minus 1 plus 1 becomes n, and so on. This is our expression for the second iteration, the third iteration, the fourth iteration, and so on. All our sums are finite. At some point, we will run out of material to iterate, and the last or the bottommost expansion shown over here is basically or essentially the very first one, the first expansion, where the symbol n is replaced by 1. 1 plus 1 is 2, 2 to the third power, n becomes 1, 1 cubed plus 3 times 1 squared plus 3 times 1 plus 1, and so on. This is the step number 2. Done. Is quite mechanical, straightforward. A proverbial middle school student can follow it. Step number 3. We sum all these equations, and what do we witness? We witness again a wonderful tsunami wave of favorable cancellations. Northeast to southwest, n cubed and n cubed is gone. N minus 1 cubed and n minus cubed gone. N minus 2 cubed, n minus 3 cubed, and so on. 2 to the third is somewhere here. And once we are done with these cancellations, what material does survive these cancellations? Well, the material that survives these cancellations is the following. On the left-hand side, the only term that survives is n plus 1 cubed. We know this is a fixed material. Forget about it. We know how to deal with it. On the right-hand side, the leftmost column gets what? It almost gets wiped out, except for the term n1 cubed, which is 1. We leave it alone, plus. Now we take a look at the second column more closely. What does this column over here, when all its terms are summed, look like? N squared plus n minus 1 squared plus n minus 2 squared. Well, this is precisely our sum S2. If we look at this sum, at these equations top to bottom, this is the sum S2 spelled in reverse order, or backwards if you will, which nothing is wrong with that spelling also. This is a good thing to manipulate in your mind. If we go from the bottom to the top, then this is precisely our sum spelled in the traditional forward flow order. 1 squared plus 2 squared plus 3 squared, and so on. Thus we have 3 copies of S2. What is this column over here? This column is our sum S1, n plus n minus 1, or in reverse order, 1 plus 2 plus 3 plus so on and plus n. So 3 copies of S1. And what do we have in the rightmost column? 1, 1, 1, n copies of 1. This is our sum S0 in disguise. Thus, we produce the food for the step number 4. This is our equation that is again linear in the sum that is sought after, sum S2. And now I will take a short break, erase this board, put this expression front and center, and we'll take that final computation home. Good stuff. In this segment, we will bring the final computation home for the finite integer power sum S2, and we all understand where this equation comes from. And now, according to step number 4 of our algorithm, all we have to do is isolate S2, and solve this equation for the sum S2. We shall have as such, 3 times S2 is equal to n plus 1 cubed minus 1 minus 3s1 minus s0, which is n plus 1 cubed minus 1 minus 3 n times n plus 1 over 2 minus n. This is expression for S0. This is expression for S1, which is already known to us. We computed it in the previous iteration of the application of our algorithm. And then all we have to do now is basically spell out we have to fight it out with this expression over here. We expand the n plus 1 cubed. Well, we obtain n to the third power plus 3 n squared plus 3 n plus 1 minus 1 minus n minus 3n squared plus 3n over 2. Here I just spelled out 3 times the sum S1. We see negative 1 and positive n cancel out. Negative n and 3n become 2n. And what do we have? Here we have n to the third power plus 3n squared plus 2n plus 2n. This is all this material is gone. Minus 3n squared plus 3n over 2. So far so good. And now we simply bring all this mess under the same denominator too. And what do we obtain? We have 2n cubed plus 6n squared plus 4n minus 3n squared minus 3n, all divided by 2. And what do we have? Let's see. 3n and 4n cancel out, leaving us with 1 copy of n. 3n squared and 6n squared cancel out, and what do we have? We have 3n squared. And in the end, what do we have? We have 2n cubed plus 3n squared minus plus n over 2. And from here it follows what? Once we have this expression, we simply take our 3 times S2, divide both sides of this equation by 3, and what do we have? We obtain, let's write it down over here, S2 is equal to 1 copy of n can be safely carried out from the numerator. So we have n over 2n squared plus 3n plus 1 over 2. 2n squared plus 3n plus 1 over 2. And the last thing is to factor this quadratic polynomial. This is quite straightforward to do. In some sense, we will leave it as an exercise to our viewers. This will be n plus 1 times 2n plus 1 over, I'm sorry, this is 6 over 6. This is our expression for S2 again. This is what we were aiming for. Now we know the alternative expression for the sum S1. We know an alternative expression for the sum S2. And now that we understand how that process worked out for the sums S1 and S2, let us apply this algorithm to the finite integer power sum S3. In this segment, we will apply the algorithm that we described at the beginning of this episode to the process of recovering an alternative expression for a finite integer power sum S3. And here, using the step number 1 of that algorithm, we take the expression n plus 1, raise it to the power p plus 1, since p is equal to 3 in this case, p plus 1 is 4. Consequently, the expression to be binomially expanded is n plus 1 raised to the power of 4. That expansion, again, is mechanical. We do not really to think much. It's just a mechanical computation. That expansion comes out to the 4th power of n plus 4 copies of n cubed plus 6 copies of n squared plus 4 copies of n plus 1. So these numbers over here are known as binomial coefficients. And now that we carried out that expansion, our second step of the algorithm that we described at the beginning of this episode calls for creation of n minus 1 copies of this expansion, and for the iteration of each copy via n substituted into n minus 1. The question is, however, should we really do that? And that is a honing question. Raise your hand if you think that we should go through all these steps that we described in our algorithm originally. Here, all the people who raised their hands were not paying attention because evidently we do not really have to do it. Why? We don't have to do it precisely because our expansion that we obtained over here contains the entire blueprint or carries all the information that we need in order to solve the problem at hand. In other words, the scope expansion driven expansion, the binomial expansion shown over here, contains all the information that we need in order to evaluate the finite integer power sum S3. Which way? What does it mean? Well, we already know that once we construct all the remaining n minus 1 iterations of this expression shown over here, sum them up, cancel them out, what will we have? We know that the term n4, let me use maybe the red chalk that you guys see, the term n4 will collapse into what? Into the 1 raised to the 4th power, but 1 to the 4th power is 1, so this will become 1. Here we know that this term will survive as it was, n plus 1 to the 4th power. Here we will have what? We will have 4 copies of our sum S3. So right away we write 4 times S3 plus then what? Well, we just again read it like a blueprint. 6 copies of the sum S2 plus 6 copies of the sum S2 plus what? Plus 4 copies of the sum S1 plus the sum S0. We already know that much. So basically in one step, we know that this one becomes S0, this becomes S1, this summand becomes S2, and this is our sum sought after S3. And in one beautiful step, we come up with a final expression which we are, a final equation which we are to solve for S3. And what do we have? Let's write it down. 4 copies of S3 is equal to n plus 1 to the 4th power minus 1 minus 6 copies of S2 minus 4 copies of S1 minus 1 copy of S0. That much we understand, and remember that in the step number 4 of our algorithm, after we solve the equation for the sum sought after, for the sum S3, we are to roll through all the intermediate S p minus 1, p minus 2, and so on sums and substitute these sums with their personal alternative expressions in order to express the sum at hand or the sum sought after through the material which contains nothing but our favorite symbol n. And this is exactly what we can do once we have this expansion, once we have this expression over here. We know what is the sum S2 as a function of n, we know what S1 as a function of n, and we know what is the sum S0 as a function of n. And again, on the one hand, I do not want to insult your intelligence by going through all this middle school arithmetic. On the other hand, just to make sure that there are no secrets in mathematics, but there are mysteries, and we want to show how this computation can be carried home in the next short segment. In this optional segment, we bring home the final computation for an alternative expression for the finite integer power sum S3. If you understand how these things work and you can complete that task on your own, then feel free to fast forward. And for the rest of us, over here on top of the board, I wrote down the equation that we obtained in the previous segment for the finite integer power sum S3. We understand where did this equation come from, and here we roll through that equation and replace the value of the finite sum S2 with its own alternative expression. We replace the value of the sum S1 with its own alternative expression, and we replace the value of sum 0 with its alternative expression. We know what these expressions are, and when we carefully do that, we already sense that something is quite amazing going on. Here in front of the sum S2 we have the factor of 6, and we remember what was the alternative expression for the sum S2. It was n times n plus 1 times 2n plus 1 over 6. So 6 in the numerator and 6 in the denominator cancel out, and we have this expression over here. And the alternative expression for the finite sum S1 that we deduced earlier is what? N times n plus 1 over 2. 4 in the numerator, 2 in the denominator cancel out. We have 2, this factor right here. And this computation is shown over here. The sum S0 is basically n, and this expression over here should be understood by everyone. Now we carefully analyze this string of symbols, and what do we see? N plus 1, n plus 1, n plus 1, and if we take this negative n and this negative 1, what do we have? We factor out negative 1 and we get n plus 1. Consequently, we factor out n plus 1, and what do we have is in the parentheses as a result? N plus 1 to the 4th power becomes n plus 1 to the 3rd power. N plus 1 factor is gone from here, n times 2n plus 1 here. N plus 1 factor is gone, negative 2n, and negative 1 is left over from what? Negative n and negative 1 shown over here. Next, we concentrate on this string of symbols over here. And what do we see? Again, if we factor out negative 1 from here, what will we have? 1 plus 2n. Factor out 1 plus 2n from here, and what do we get? This is captured over here, all these things, and now this becomes what? 2n plus 1 times n plus 1, with a negative sign in front of it carefully. Now what do we have again? N plus 1, n plus 1, n plus 1. Factor it out. When n plus 1 in front of this parenthesis collides multiplicatively with n plus 1 that we factored out, it becomes n plus 1 squared. And what do we have left over inside the parenthesis? N plus 1 squared minus 2n plus 1, as shown over here. And now we simply unwind this expression over here. What do we see? N plus 1 squared becomes n squared plus 2n plus 1 minus 2n minus 1. Here, negative 1 and positive 1 cancel out. Negative 2n and positive 2n cancel out. And what will survive this perfect wave of cancellations? Only n squared. Thus, we have all this beautiful mass collapses into n plus 1 squared times n squared. But what is this? This is another name for 4 times the sum S3. Consequently, if we divide both sides of this equality by 4, we obtain an alternative expression for our finite sum of powers of the integers, each of which is raised to the 3rd power, is shown over here, n squared times n plus 1 squared over 4. And if we juxtapose this result against the result that we obtained for the sum S1, then we will see that, amazingly enough, this alternative expression for the finite sum S3 is actually the perfect square of the alternative expression for our finite sum S1. Clearly, n times n plus 1 divided by 2 squared will be precisely this expression. Now that we understand how our algorithm works for the finite sums S1, S2, S3, in the next segment we will show several more expressions for the finite sums S4, S5, and S6. It is safe to say that pretty much all academic information across mathematics, theoretical physics, and computer science works in the following way. The future academic or the new academic information is built up on top of the previous or the existing academic information. In our specific case, the results that we obtained for the finite integer power sums S1, S2, and S3 represent the existing academic information, and we recommend that as a good exercise for all of our viewers should obtain the results, the similar results for the finite integer power sums S4, S5, and S6 on their own. I think that when I was carrying out or applying the algorithm that I described at the beginning of this episode to the finite sums S4, S5, and S6, I did not make any mistakes. I hope that the expressions that you see over here, just to make sure for the finite sum S4, the expression is the following. In the numerator, we have n times n plus 1 times 2n plus 1 times 3n squared plus 3n minus 1. In the denominator, we have the number of 30, and you can actually see over here that if we carve this little piece over here, what do we have in reference with the sum S2? Exactly, this will be the sum S2 divided by 5 times this polynomial right here. For the finite sum S5, or the sum of consecutive fifth powers of the positive numbers 1, 2, 3, and so on, we obtain n squared times n plus 1 squared times the polynomial 2n squared plus 2n minus 1 over 12. And what do we see over here? Yes, exactly. We see the sum S1 lurking in the bowels of the sum S5. Apparently, this is what? This will be the square of the sum S1 and then 1/3 of that square taken over here. So the 12 is produced. In the denominator, we have 12. For the sum, for the finite sum S6, we have the following expression. The 6 powers of consecutive positive whole numbers, 1, 2, 3, and so on, come out to, again, n times n plus 1 times 2n plus 1 in the numerator times this mighty fourth degree polynomial, 3 times n raised to the fourth power plus 6n raised to the third power minus 3n plus 1, that's in the numerator. In the denominator, we have the number 42. And again, here we can also see that we can carve up that expression over here as what in terms of the sum S2. This is sum S2 divided by what? Divided by 7 times this fourth degree polynomial. And again, I think that I did not make any silly arithmetic mistakes. If I made any mistakes, then I apologize, and feel free to comment in the comment section of this episode. This way you know that Roman is just a human who makes mistakes or makes errors all the time. This way you guys know that I'm not some deepfake AI image, but there is a reason why I am asking you to compute the alternative expressions for all these sums, because all this work that we have done so far will become the foundation for our next mathematical problem, S2M29. As a hint for the next challenge, or the mathematical problem S2M29, let us analyze what we have done in this episode from the following standpoint, from the following angle. For example, for the sum S1 shown over here, let us compute the power in which our usual suspect n participates in this particular shape of the alternative expression for that sum. 1, because here n is raised to the first power, plus 1, because n is raised to the first power, comes out to what? 1 plus 1 is 2. So here, let us write down number 2 as in small parentheses. Probably too small for you guys to see, but in your own paperwork, you can do the same. So write down the number 2 and the number 1 over here for the sum is 1. In what relationship do the numbers 1 and 2 exist in simplest possible terms? Well, 2 is exactly 1 plus 1. In other words, we can say that as a closed form expression, the sum S1 shown over here can be expressed or can be written down as what? As a polynomial of degree 2. Let us analyze the sum S2 in the same fashion. What is the power? What is the highest power of our upper boundary of the sum n? 1 plus 1 plus 1 comes out to 3. So here I'll write the number 3. So what is the simplest relationship between the number 2 and the number 3. Well, the number 3 is 2 plus 1. Again, we can say that in somewhat perhaps vague way, the alternative expression for the sum S2 shown over here can be expressed as what? As a polynomial in n, which is in which power, of which order? Of order 3. 1 plus 2 is 3. Likewise, let us analyze the alternative expression for the sum S3. 2 plus 2 is 4. So here we have number 4. And in what simplest relationship do the numbers 3 and 4 coexist? Well, 3 plus 1 is equal to 4. Again, we can say that the alternative expression for the sum S3 can be represented as a polynomial in n of degree 4. 3 plus 1, degree 4. Likewise, for the alternative expression for the sum S4, let us compute the highest power of n in this case. 1 plus 1, 2, plus 1, 3, 3 plus 2, 5. So here we have again 5. Here we have 5. So what is the simplest relationship between 5 and 4? Well, 4 plus 1 is 5, and the alternative expression for the finite sum S4 can be represented as a polynomial in n of degree 5, or degree higher exactly by 1 as the index 4 over here. What about the alternative expression for the finite sum S5? Same thing. 2 plus 2 is 4, plus 2 is 6. So here the highest power of the symbol n is 6, so the alternative expression for the finite sum S5 can be represented as a polynomial in n of degree, which one? Of degree 1 higher than the index of the sum S5, degree 6. What about 6? Well, we can already predict that this will be an expression or a polynomial in n of degree 7 most likely. Let's compute. 1 plus 1, 2, plus 1, 3, 3 plus 4 is 7. Bingo, 7, we have our number. So the finite expression for the sum S6 can be represented as a polynomial in n of degree 7, which is precisely 1 higher than 6. As such, inhale all this information, and in the mathematical problem S2M, let me write it down here, 29, our next challenge will be the problem 29. Come up with a similar but different way to evaluate or to find the alternative expressions for our sums SP of the shape k raised to the fixed power p, which is known and fixed ahead of time, using the information that we generated in this episode. This is it for this episode. Thank you very much for your time. Thank you for watching. I will see you in the next episode, in which I will present my solution of the mathematical problem S2 and 29.